Hi everyone, just doing a quick video basically going through this step question. It's a current one I've just worked on. I tend to like doing the ones which I've done recently, especially when they're fresh in my head because it's easier to explain. You remember your reasoning. But yeah, anyway, let's have a look at this. The reason I like this, by the way, is it's in step 3 and you just need A2 maths to differentiate that and that because it's stationary points with implicitly defined functions. That's just A2 maths. And then for the last part, you don't even need A2 maths. So you could definitely solve this just if you've ever tried to solve a system of three, three simultaneous equations here. Well, it's sort of like you're only finding x and y actually, but you've got cubes and squares. So you're just, solving a system of equations. That's always done in the same kind of way. If you ask me, you eliminate the letters, and that's what we're doing throughout this actually, just eliminate the letters so you've got it in terms of one variable. But anyway, let's give it a go. So implicitly defined, show that if the curve has two stationary points, then that's true. Well, that looks like the discriminant to me, so I'm thinking maybe this is about the discriminant of a quadratic at the end. Finding stationary points, we're going to have to differentiate this. It's an implicit function. We're going to have to differentiate implicitly. As soon as I'm looking at this, I'm writing it down. Oh, product rule there. I'm going to differentiate the bx, that gives me a b, with respect to x. Remember, I'm doing d by dx to everything here. So differentiate bx, you get b, times it by the other side undifferentiated, plus differentiate y, you get dy by dx, times it by the other side undifferentiated. That's product rule. And then plus 2cy dy by dx, that's just the standard approach when you're differentiating implicitly. And then differentiate the 1 as well, it differentiates to 0. Okay, rearrange this. Let's have this as dy by dx times by bx plus 2cy, and that must equal the other junk over there, because what I'm going to try and do here is I'm going to try and find out a fact between x and y for where the stationary points are. And the stationary points occur when dy by dx equals 0. So what have we got here? We've got minus 2ax minus by over bx plus 2cy, and that should equal 0 on the lines of stationary points. So times that over there, you're going to get minus 2ax minus by equals 0. So indeed, you get y equals, for example, minus 2ax over b. Yeah, what's that shown you? It's shown you the stationary points of this curve will lie on the line y equals minus 2a over b. X, yeah, so a straight line in other words. Now just to show you that's true, because I just typed this in, I just made A, B and C, all of them 1 each, yeah, and I drew the line y equals minus 2x. Sure enough, the maximum minimum values, the turning points, occur on that straight line. Yeah. So how are we going to find where these turning points are? We're going to have to basically solve this system of equations simultaneously. Yeah. And so let's eliminate a variable. Now I'm going to get rid of the y's here. So I've got ax squared. Might as well. It doesn't really matter which one you eliminate here, but ax squared plus bx, oh, I need a y, well that's just times by minus 2ax over b, and then plus a c, y squared, well y squared is just 4a squared x squared over b squared, and that should equal 1, yeah, because I'm just finding where the original curve hits that straight line, because that will be my turning points. And remember, I don't need to find the turning points here, I just have to show that if there are two turning points, that's true. Yeah, so let's just tidy this up a bit and talk about what we're going to do next. We've got x squared. I'm going to group the x squareds because then I can see I've got a plus 4a squared c over b squared. Yeah, that's going to cancel with that, isn't it? And then I'm going to have minus 2a. Oh, look, and I've missed an x squared. Yeah, x squared. So yeah, actually I should have subtracted that to that. I'm just going to, sometimes you take back a line because you're like, there's a quicker way of simplifying it. This has got a squared minus 2ax squared. Always look at things like this as well. That's poor from me. So minus a x squared plus all this nonsense. So 4a squared c over b squared. Let's just factorise out this x squared as well. Times by all of that. Minus 1 equals 0. Yeah, what is this? This is this is just a quadratic. Let's tidy it up actually a bit. I quite don't like that b squared in there, so I'm going to times everything by b squared just because it would be nice to have it without any fractions. Minus ab squared plus 4a squared c minus b squared equals 0. Yeah, now we just need to make sure that this has two solutions, because if it has two solutions then it'll have two stationary points, if you see what I mean. We don't need to know the solutions. It didn't ask us for that, just to ask us to show a condition was true when those points are stationary. So this seems like an ideal place to use a discriminant. If it's got two solutions, then, you know, if I can write in inverted commas and not get confused with the totally different meaning of a, b, and c in this question, but b squared minus 4ac in a typical quadratic, it should be greater than 0. Yeah. So what's your b squared here? It's 0 minus 4 times by a, which is this, times by your c, which is that. Yeah. And that should be greater than 0, we hope. Okay, the minuses are going to cancel. We might as well divide by 4. We can also safely divide by b, actually, can't we? Because look at this. Like b, a, and c, none of them are 0. So I don't have to worry about division by 0 or whether it's positive or negative over an inequality. Oh, I do need to worry about whether it's positive or negative, actually, but I can divide by positive b squared here, so it's guaranteed positive. You do have to be careful with that, but because of that, I can get rid of that and that straight away. And I can just say, okay, minus ab squared plus 4a squared c is bigger than 0. Now I was trying to show b squared minus 4ac is bigger than 0, wasn't I? I can safely divide through by the a, because I think they said a was bigger than 0. Lovely, lovely stuff. A is bigger than 0, so I don't have to worry about that being positive. Negative, because it's definitely positive. And so I have minus b squared plus 4ac is bigger than 0. So I guess 4ac is bigger than b squared. Hopefully that was the right way around. 4ac is bigger than b squared. Brilliant, that's exactly what I had just written the other way around, didn't I? Yeah. Cool. Okay, so that's the first one, yeah? I think that was worth about 4 marks. I seem to remember that part 2 was worth about 10 marks. Part 2's the hardest bit, it really is. You get to that bit, that regular occurrence in step where you hit a wall, I think. It's got that moment in the question where it's like, yeah, it's just got super difficult. I got fine to here, and then getting from here to here, you know, that was like, okay, thinking time, 5 minutes, like, you know, going nowhere as well, and then suddenly it was like, I think that's it. But yeah, I think I could have easily lost marks on this bit in exam conditions. I'd hoped to get 1 and 3 right, though, and half the marks for 2 at least. And it goes to show that you don't always have to rely on previous results, yeah, in step questions. Sometimes you do, you know, other parts help you, but not always. And quite often they show you the crucial bits. They do try and help you in a weird kind of, it's still very difficult way. Okay, so this time, very similar looking question, really. Show that the x coordinates of the stationary points satisfy that. So this time we haven't got to show a condition holds for the stationary points. We've got to find the quartic in this case, which is satisfied by the solution to where, you know, the x coordinates on the stationary points. Okay, so once again we're just going to have to differentiate implicitly. Plus, okay, 2bxy plus bx squared dy by dx, and then plus c equals 0. Yeah, same thing again, dy by dx equals, I hope you don't mind me going straight to this bit, because it's, yeah, worth saving time in these papers, minus 2bxy minus c over 3ay squared plus bx squared. Okay, that's what we're going to have here. So that's kind of nice. So we're just going to let the top equal 0, because that's just going to fly over there, and we're going to get c equals minus 2bxy. Okay, that's kind of an interesting result. So we're going to have to go back to our original equation now, which is over here, and we're going to try and, you know, eliminate y. So we've got it solely in terms of x, because that's their quartic. Okay, so we've got a times by, well, y cubed, let's quickly note that y cubed is c cubed over minus 8b cubed x cubed. Yeah. Okay, so that makes it slightly easier actually for the next bit, because I can just say, okay, ac cubed over minus 8b cubed x cubed plus bx squared, and then y, well, that's actually minus 2bx over, sorry, c over minus 2bx, dear oh dear. And then we've got a plus cx on the end equals 1. Yeah, and we're trying to simplify this and turn that into that. Well, once again, it's just really algebra, this. I guess the best thing to do first would be times by minus 8b cubed x cubed. Get rid of those horrible fractions. So we got you got ac cubed plus bx squared c times by, now what we're going to have be left with there, 4b squared x squared. And then we're going to have plus c x to the 4, well, should we say minus 8? Minus 8b cubed. Let's rub out that plus as well. Minus 8b cubed, x cubed, x to the 4, sorry. Oh, and I really want to put a c in there. Minus 8bc, b cubed c, x to the 4. It's, it's cumbersome, it really is. Minus 8b cubed, x cubed. Cool. Okay, now have a careful look at this. We've got an x to the 4, we've got an x to the 4, and look, that's actually 4b cubed x to the 4, 4b cubed c x to the 4, minus 8b cubed c x to the 4. So we've got minus 4b cubed c x to the 4, that's the negative of what they've got, so we'll probably swing it round. And then we've got plus 8b cubed x cubed if we add it over the equals. That's the opposite of their sign, which is nice. And then plus ac cubed equals 0, and the result follows. We just times by minus 1, and so we've done it. So that's all good. Let's just write down their result as good practice and all that. I can't be bothered either, but we can see the work's been done. But please do in the exams. It finishes the argument. Okay, so there we go. As required, we'll draw a little square even and colour it in just so they can see. That's the end of our proof. Okay, show that if the curve has two stationary points, then this is true. This is difficult. This is where you've got to be prepared. This is one of those things you've got to be prepared to do on step questions. Like just sometimes think, well, how, really think beyond what you're normally asked to do. Even if it sounds like it's going to be a huge amount of work, well, yeah, that might be what they're asking you to do. Because what we've really got to do here, I mean, this is a quartic. There's no two ways about it. So, do you know the conditions for a quartic having a quartic can have, there's no doubt about it, a quartic can have no solutions. It can look like that, yeah, or even it can just look like that. Remember, it doesn't have to have two turning points. It can have like just one solution. It could have, what we're interested in is two solutions, yeah. It could have, could it have only three solutions? Yeah, if one of them's repeated like that, it could do that, or it could have four solutions. Just going through the line, yeah. And notice I've always been drawing them as positive x to the 4 there. You do have to think about the negative case as well, yeah. But can you see the one we're interested in is this one, yeah. Now what do you notice about quartics in that situation? Just think for a second. Well, if this is a right, as you might describe it, as a positive x to the 4 quartic, as I've drawn it, then you need your turning point with a y, a negative y value, yeah, a negative y on your turning point, yeah, and then it will definitely pass through the x-axis, and you've guaranteed that you've got at least two solutions, yeah. Now you do have to be slightly careful that you're not going to get four solutions, yeah, because you could get four solutions from this. Actually, I've just thought about it, and I'm actually considering the wrong case, aren't I? Because let's just go back and have a little think. Am I considering the right case? Yeah. Oh yeah, because we're looking for the turning points here, yeah, and we've found that they will definitely satisfy this quartic, and we want our quartic to have just two solutions, yeah. So if we take our quartic curve and make sure it's got a negative y component when it's a right way up quartic, that should really help us. We've just got to be worried about this coming back down though, but we might, we'll have a look. Let's just have a look what happens when we differentiate, because that's when you suddenly realise you've struck gold. Okay, so what I'd said next was consider, so this is the next part of part 2, it's a difficult bit. Consider the curve, consider. Right, y equals 4cb cubed x to the 4. Consider the quartic basically, and the fact that it has just two turning points, two solutions, yeah. So I'm thinking about the fact that this has just two solutions. Okay, find its turning points. Let's think about its turning points. And as soon as you differentiate, you realise, something very interesting happens. dy by dx is 16cb cubed x to the 3 minus 24b x squared. And then that differentiates to 0 because they're just constants, yeah? And we're finding where this is equal to 0, so it's obvious to take a big factor out of that, of 8. Is this 8b cubed as well? Have I miswritten that? You know what it's like, it's easy to miscopy such a long expression. Yep, it was b cubed. So let's write that there. So 8c, and it's got a c, oh no, it hasn't got a c in it, second term though, I don't think. Let me just check my notes actually. No. Okay, that's why they're different terms and can't be combined, of course. 8c, sorry, it's 8b cubed, x squared, and then 2x minus 2cx minus 3. Let's just tidy that up, 2cx minus 3. Lovely, and that equals 0, yeah? What does this show us? Now here's a really interesting bit for me, and I'd love to hear your thoughts about this, because this is what, this is my reasoning. This has a stationary point of inflection and another turning point, yeah? In other words, our quartic is definitely shaped like this if it's a positive x to the 4, or it could be shaped like this if we want to insist that it's got two solutions, if it's a negative x to the 4. What I mean is there's a turning point, and the turning point is, a point of inflection. It's not a turning point, is it? A point of inflection which is stationary. It doesn't really turn like I don't think it would strictly meet the definition of a turning point. It meets the definition of a stationary point though, because the gradient is 0 there. I think turning points really are just maximums and minimums. But let me know once again in the comments if you want to have an argument about definitions and stuff. It's always interesting, and I'm always happy to learn as well. So yeah. I figure, basically, if we want to make sure this quartic has just two solutions, we're in a really strong position now, because we know that one of the turning points on our quartic is definitely going to be a point of inflection, which means we can not worry now and just think, well, just make sure now that in this case, now remember the original curve, this was the equation, yeah? We already know that b is greater than 0. I think they told us that in the question, I think. If I remember rightly, yeah, b is greater than 0, and neither a nor b nor c is 0. But we just have to consider if c is bigger than 0, then we've got this case, and we need to make sure the y coordinate at the stationary point is negative. Now that isn't as bad as it sounds, because can you see here that x equals 3 over 2c for this bit, but x equals 0 for that bit. Oh, and I haven't really justified why this is definitely a stationary point of inflection, yeah? Basically, if you ever get square factors, like when you get dy by dx equals 0, maybe it equals like x minus 2 squared x plus 3, yeah? That would show you every time that there's a turning point at x equals minus 3 here, but a stationary point of inflection here. And you can justify it really quickly, I think, if you just think about locally around this point, yeah? Like, let's say you're at 1.99, and you're at 2.01, yeah? Basically, this is definitely going to have a positive gradient, yeah? But just to the left and the right of, like, x equals 2, this sign is not going to change after you square it, yeah? So you're definitely going to have, in this case actually, a positive gradient both sides of that stationary point, which is only possible if it's a stationary point of inflection. In other words, this curve, which obviously goes through, like, it's a quartic, but its turning points are at minus 3 and 2, it must go through like this, and then when x equals 2, you've got, x equals minus 3, you've got a turning point, yeah, so maybe it does something like that, but then at x equals 2, you've got something like that, yeah, and you can see it because the gradient's positive both sides, so this is just on this example, and the same thing works here when x is 0, yeah, can you see when you pick a value like minus 0.1 and positive 0.1, values really close to the turning point at x equals 0 here, you're going to have a gradient which is, in this case, negative both sides, yeah? And it's because when you've got, like, say, x is 0.1 0.01, yeah, something which makes this really small. This is going to be -3 times by basically a positive number, and when x is 0.01, this is going to be -3 almost times by a positive number, and so you're going to be negative on your gradient either side of that point. So that was really interesting, yeah. So that's why this trick I'm about to do works. Basically, I can now say there's only two possible cases. When c is greater than 0, we need a negative y coordinate, which means we just need to plug this back into the original equation and make sure it is less than 0. But if c is the other way, if c is negative, then we just need to basically do the opposite and make sure the y coordinate is positive. Yeah, y coordinate must be positive. So curve sketching, once again, is a massive skill in this exam. There's no way you're getting through it without curve sketching. I think you've got to be a great graph sketcher. And it's practice. It really is practice. Okay, so let's let's plug this value back in and insist that y is less than 0. Let's do it case by case. So assume c is less than 0. C is bigger than 0. Then y, which equals 4cb cubed multiplied by 3 over 2c to the 4 minus 8b cubed multiplied by 3 over 2c cubed minus ac cubed. We want that to be negative, so less than 0. Yeah. Now I'm just going to turn it into their answer, I hope. Now once again, what can we divide by straight away because we know it's not 0, it's bigger than 0. Is it b is greater than 0? Here it is. So good, because that gets rid straight away of, oh well, actually no, it doesn't quite. It's a shame we can't do that yet, but we will. Okay, what have we got here? What did I do? Let's have a look. So this becomes, we're going to get, try and do this as efficiently as possible. 2 to the 4 is 16, but you're going to have a 4 over 16, so it's going to be over 4. The c's are going to cancel, well, one of the c's is going to cancel, and you're still going to have a c cubed on the bottom. On the top, you're going to have 81b cubed. And that's all good. And yeah, good. Okay, minus 8b cubed times by 27 over 8c cubed. Let's cross out the 8's. Minus ac cubed. And we want that to be less than 0. Okay, lovely. Might be time to multiply through by 4c cubed, because we do know something about c is bigger than 0. Yeah, that's lovely to know, isn't it? So we can safely multiply by 4c cubed and we don't have to worry about the sign. We're going to have 81b cubed minus 27 times by 4, sorry, I'm timesing it by 4c cubed, so 108 b cubed, lovely, that's got rid of the c cubed there, minus 4ac to the power of 6 is less than 0. And what is that? Minus 27b cubed minus 4ac to the 6 is less than 0. And if I times through by minus 1, I get 27b cubed plus 4ac to the 6 is bigger than 0. Is that what I was looking for? Something like that? I hope so. 4a to the 6 plus 27b cubed is greater than 0, yeah? Now, I did it for the positive case. I really should do it for the negative, but it does work exactly the same way. Assume c is less than 0. It annoys me when you know it's going to work, but you have to still write it down. Then, you know, that's going to be exactly the same. When did we start using these results? Maybe, when I times through by... Let's just star that bit here and say, then from here, when you times through by 4c cubed, you're going to get 81b cubed minus 108b cubed minus 4ac to the 6. Well, that's now going to be greater than 0 because you're timesing by a number which is negative. But, of course, at the end, it all sorts itself out, because what do we get now? Let's have a little look. We're going to get minus 27 b cubed. Oh, but hang on a second. No, you've got to go back to the start of the argument because this should be greater than 0. Yeah, and that's why it works out. Sorry. Let's make it real clear for the examiner as well then. Then y is greater than 0. Then y must be greater than 0. In order to have, remember, why are we doing this? In order to have two stationary points, because this will definitely have two solutions to that equation. And so this just guarantees it. Then y is bigger than 0, and basically everything works backwards. You get to that point where you're like on 81b cubed over 4c cubed minus 8b cubed times by 27 over 8c cubed. I'm so annoyed that I've got to write this down. Always away. That's going to be bigger than 0. Times by 4c cubed, you get minus 27b cubed minus 4ac to the 6 is less than 0. Do you see what I mean? I'm trying to point out the critical steps in the argument where the minus undoes itself. And hence 27b cubed plus 4ac to the 6 is greater than 0. Cool. Convince yourself of that. I was almost bored doing that bit, but can you see that bit's worth 10 marks? Now, the very last part, part 3. Now, I hope some of the students who haven't done A2 maths yet can still have a go at this part, because honestly, you don't need anything from the previous parts really for this. You just need to be comfortable with the idea of solving simultaneous equations. So what am I going to do? I'm going to think, well, let's eliminate a letter. These ones look easier to rearrange. The first one looks most awkward. So what can I tell from that? I can see that minus 2bx squared y. And I'm trying to introduce another x here, is minus cx, yeah? Oh, sorry, is cx. Now, why have I written it down like that? Well, because I've got cx there. That means immediately I can replace that with like x squared y, and why would I want to do that? Well, because I've got a bx squared y there, yeah? Now, it just seemed like a nice fact, an easy way to deal with that first one. And the second one, well, 3ay squared is minus bx squared, yeah? Now, why do I want to do that? Well, because then I think I'm in a strong position to actually get rid of all of the letters of one type here. If we just look at this and call this one a, I thought, well, okay, first I can see that ay cubed plus, okay, bx squared y plus cx equals 1. Well, let's look at the bx squared y first, yeah? This is going to be 3ay cubed, isn't it? If this is minus bx squared y, yeah, just times both sides by y, and you can see then that you can replace this with a minus 3ay cubed, which is what I did. In other words, I'm going with getting rid of all the y's here, yeah, and cx, well, that is minus 2bx squared y, yeah. I'll just write this down for the moment, because I think I can get rid of that now because of the minus bx squared here. So that's just double that, yeah? And so you get minus 2ay cubed here. And then what are you going to get here? Well, the minus 2bx squared y is going to become, if I just replace that with double that, minus 6, minus 2, plus 6ay cubed. And that should equal 1. Okay. We can actually solve this, can't we? Yeah, show that if this has a solution, then that's true. Well, let's actually just solve it. Like, 4ay cubed is 1. And so y is 1 over 4a cube rooted. Yeah? Okay, that doesn't look particularly nice, but, if I've got y, then presumably I can find x, yeah? Now, let's just look at, for example, this, and this should tell me what x is. Minus 2b. Where is the one where it's most obvious with x? Let's have a look at this original, yeah? And then you can just see that x is going to be minus c over 2b y. And so that equals, it's not very pleasant, this. I didn't find it very pleasant writing this down. I kind of winced as I was writing it down, like, ooh, this doesn't look like a nice way to write it. What an ugly way to write it. Yeah, indeed, that's what I wrote it down as. And then I just thought, well, okay, now I can find a condition which is an equality as well. I always think, if it's an inequality, why is that? If it's an equality, how can I get those in maths? This is basically, I'm just finding a condition on A, B, and C. Yeah, I've found where the solution is. If I plug it back into any one of these equations, it should hold. Yeah. Now I'm not going to plug it back into the middle one because I've got a sneaky feeling it's going to end up being 0, seeing as I used it to work out the x there. Yeah. So if I plug it into one of the other two, and I thought bottom one looks as good a thing to plug it in as anyone. So all I'm going to do is just replace y and x with this bottom equation, because we've solved the system of equations. We've found where these three surfaces, not surfaces, sorry. We've found where these three, yeah, it's like a like well, it's we'll draw pictures of it afterwards and have a look. That's what we'll do. We're looking at like non-linear geometry here, so it's not about like planes hitting each other, because they're not planes. They're kind of like yeah, they're strange surfaces, I think. But anyway, let's finish this question off, because I'm getting to the point where I'm quite tired. Okay, so all we've got to do now is plug it into that third one. 3ay squared plus bx squared equals 0. Let's write that down. 3ay squared plus bx squared equals 0. And so I've got 3a times by, I'm going to just leave the 1 alone actually and write that as 4a. And then I can write that to the power of 2/3. Yeah, 1 to the power of anything is 1, so I've just done it like that. Okay, plus bx squared. Now, okay, plus b times x squared. Okay, so that's just going to be this squared. Well, firstly, that b, well, we're going to have c squared over 4b squared, and then it's going to be 1 over 4a to the 2/3 again. That pesky 1 over 4a to the 2/3, and that equals 0. Yeah, and I'm just trying to turn this into the answer. Once again, the algebra's fiddly, but you can get there. Yeah. If it's just algebra, it's just algebra, if you know what I mean. Like, you know, it must be a way. Okay, so I did that first. I think I then moved that over here, so I had 3a over 4a to the 2/3. Remember, 4 and the a is to the 2/3 here. Plus, no, I moved the c squared over because I wanted to basically cube both sides, like without worrying too much about it, because I wanted to get rid of the cube root there. Okay, over 4b, 1 over 4a to the 2/3. Well, that's really 4a to the minus 2/3. I might write it down like that. It might be less cumbersome. You know, do yourself a favour. Minus 2/3. Brilliant. Now, what can we do here? I cubed them, and also I realised that that meant that I could go on the top, if you see what I mean. So let's cube both sides. We're going to get 27a cubed over 4a all squared. I'm cubing both sides. Cube. And this is going to become, well, minus c squared times minus c times minus c squared is minus c to the power of 6. Yeah. And then you've got 64b cubed. And then you've got 4a to the minus 2, but like I say, that can easily have 4a on the top here to the power of 2. Yeah. Okay, so what have we got here? Right, well, let's get rid of some of those 4s. Can you see, firstly, the a's over here. We're going to leave left with 27a over 16. And here, we're going to be left with, well, with that 16 and the a squared, you're going to end up with minus c to the 6 times by 16a squared over 64b cubed. I'm trying to cancel as much as I can because it's a little bit annoying, this question. 16 over 64, you get a 4 there. You're going to times the 16 over, so this is going to be times by 4 times the b cubed over here. You're going to have 27ab cubed equals minus 4c to the 6 a squared. And if we divide through by a, remember none of them are 0, so you haven't got to worry about that. You're going to get 27b cubed plus 4ac to the power of 6 equals 0. And I think that's the final answer. Okay, thanks for listening. I hope it was useful as well. That's the main thing. Are you finding them useful? Yeah, let me know if you're in the comments any kind of points you'd like to make. All the best. Bye-bye.